Okay, good morning. Welcome back for the last day. Okay, so let me briefly recap what we saw yesterday. So I stated this COM, which is key in the analysis of several optimization problems encountered in quantum chemistry. For instance, the molecular orbital formulation of Hartree-Fock or Concham. So this theorem, which is a special case of the summation theorem, states that if you take two Euclidean spaces, V and W, and if G is a smooth function from V to W, and if you consider M as a set of points of V such that G of X is equal to 0, and if you assume, I forgot to mention that yesterday, but if you assume that this set is non-empty, otherwise there is not much to say, and that for all X on M, then the derivative of G at point X, which is a linear map from V to W, is surjective, then M is a smooth D-dimensional submanifold of V, and the dimension of the manifold V is simply the difference of the dimensions V and W. And we also have, this is very convenient, a very nice and simple characterization of the tangent space to the manifold at any point, and as well as the characterization of the orthogonal to this tangent space. So the tangent space is simply the kernel of this linear map, and its orthogonal is the range of the adjoint of this linear map. Okay. To show that, in fact, the orthogonal of the kernel is the adjoint of the range of the adjoint. So the argument is not difficult. I wrote it here. It will be in the notes as well, but let me just briefly go through it. So if you take, for simplicity, V equal to Rm n and W equal to Rm. So in this case, the linear map dgx is in fact a matrix with m rows and n columns. Okay. The adjoint of dgx is represented by the transpose matrix. I should say the transpose here. Okay. Which is a matrix with this time n rows and m columns. So the kernel is simply the set of vectors in Rn such that Ax equals 0, and the range of A transpose is the set of point x in Rm n such that there exists some y in Rm such that A transpose y equal to x, right? Okay, so let me show that in fact the orthogonal of the kernel is the range of the adjoint. Well, I just show here that the range of the adjoint is included in the orthogonal to the kernel. I'll let you do prove the other inclusion. So I take x in the range of the transpose. It means that there exists some y in Rn such that A transpose y is equal to x. Okay. Now I take some z in the kernel of A, and I want to check if x is orthogonal to z, in which case x will be in the orthogonal of the kernel of A. Okay. So to do that, I just compute the inner product between x and z. X is A transpose y, okay, apply to z. Then I put the matrix on the other side by just transposition. So that's y a z, but z is in the kernel, so this is 0, and so this is 0, which shows that x is in the kernel, in the orthogonal of the kernel of A. Okay, and you can show by similar arguments the other implications. Okay, so these two sets are actually equal. Okay, all right. So now this allows you to find to show that some sets are manifold. So it's a very convenient way to check when it works. It's a very convenient way to check that the set you are considering is actually a manifold, and to have a very nice characterization of the tangent space and of its orthogonal. And if you have a nice characterization of the orthogonal, you can then show that if you have a local minimum to some function defined on the manifold, or from, let's say, a real value function from V to and if x star is the local minimum of f on the manifold, then geometrically you see that the gradient of f at x star must be orthogonal to the tangent space to M at point x star, and therefore that there exists some lambda, because of this characterization, there exists some lambda star such that the gradient is of the form dg x star star applied to lambda star. Okay, this star applied to lambda star. Right? Okay, that's a geometrical characterization of the critical points. And on top of that, if as you know that this guy is surjective, its adjoint is injective, and therefore the Lagrange multiplier is unique. So in this case, you have a unique Lagrange multiplier, and perhaps it's possible to give it some physical interpretation. It's what we are going to do next. Okay. And then you recover the usual Lagrangian trick, okay? Because it's easy to show that starting from here, you can see that the pair x star lambda star is in fact a critical point of this Lagrangian, okay? And from that you can do you can infer in fact second order sufficient condition for having a local minimizer, so which can be written as follow. So if the second derivative of the Lagrangian, so the Hessian, if you want, or the Lagrangian with respect to the x variable, evaluate it at x star lambda star. Okay, so this is, if you want, in the case where V is equal to Rn, this is a Lagrangian matrix. Okay, and you apply it to VV, where V is a vector in the tangent space at x star to M. Then if this guy is positive, then x star is necessarily a local minimizer of f on M. Okay, and it's a way to characterize, for instance, true minimizers for R3-Fock. Okay, so we went through this example yesterday. It's a way to derive with geometrical arguments the R3-Fock equation. So in this example, we take V equal R and B times N. So this is the set of this is a set of matrices in which with NB rows and N columns. So each vector here contains the coefficients of the molecular orbital in the atomic basis set. Okay, and so this matrix has to satisfy C transpose SC equal identity, and this can be put in this framework by just considering this function, which goes from the set of orbital matrices, if you want, to the space of symmetric n times n matrices. Okay, and you can see that this set is simply the set of matrices C satisfying G of C equal to 0. Okay, and then you define the R3-Fock energy functional in the molecular orbital representation as a function from V to R, which associates to some matrix C, E of C, which is curly E at CC transpose. So CC transpose in this formalism is the density matrix, okay? And what you have to do is to compute the gradient of E at point C. And when you do the math, you find that this is equal to twice some matrix F at point CC transpose applied to C, okay? And the matrix F of D simply H plus G of D, which is the Fock matrix, okay? So that gives you the gradient, that is what you need here, okay? And now we compute what we need here. So we compute first the derivative of G. This is simple because this is just a polynomial. Then we compute its adjoint. We find that. We shown that this adjoint is indeed surjective. Okay. And then we satisfy all the assumptions in the theorem, and we can therefore write down the Hartree-Fock equation in this way. Okay. And we are done. Okay. All right. Okay. So now, any question about that? Oh, we're good. Okay. All right. So now let us talk about the physical interpretation of the Lagrange multiplier. Section 3.3. Yeah. So physical interpretation of Lagrange multipliers. And let us start with the famous Hellman-Feynman formula. I'm not sure of the spelling. Huh? Right? Or just one else? Hellman-Feynman formula. Okay, so we consider now, so the W Euclidean spaces and some function f from, let's say, R times V to R and D from R times V to W. And we consider not one optimization problem, but a family of optimization problem of the form infimum of f of alpha x for the x in V satisfying G of alpha x is equal to 0. And we call this infimum E of alpha. Okay? So this looks familiar if you do quantum chemistry. For instance, if you want to do a geometry optimization, alpha, so the alpha represents some nucleus coordinate, okay? And X, for instance, the matrix of molecular orbitals in the atomic orbital basis set. And in this case, for instance, you know that if you use an atomic basis set, the basis functions move with the atoms, okay? This means that the matrix, the overlap matrix depend indeed on alpha, on the nucleus coordinate. Here I just put a scalar variable, but you can put a vector here, it doesn't matter, okay, or even a matrix, you put whatever you want, okay. You just need something, you just need, in fact, a Bernard space, okay, it's very general. Okay, so in this case, you see that the function G actually depends on the parameter alpha, okay? And the Hartree-Fock energy as well. Because here, the matrix H depends on alpha as well as G. Okay, so the one body and two body electronic integrals. Okay, so you are already in this framework. Okay, and what you want to do if you want to compute the forces on the nuclei is to differentiate this function with respect to alpha. Okay. So under some assumptions that I don't want to detail here, but they are in the notes. Let's assume that I call this problem 1. For alpha small enough, so I differentiate around 0. So 1 has a unique minimizer that I called x of alpha. The unique minimizer x of alpha, and the derivative of, with respect to x of g of 0, and let's call it x alpha, yeah, is surjective. Another conclusion, the function alpha to x alpha, so it's a function from, let's say, a small interval, alpha naught, or eta, minus theta eta to z is C1, okay, or smooth. Okay. So then it's nice because we can we have an expression of E as E alpha equal F of alpha and X of alpha. Okay. Those these conditions. And now F is smooth. I forgot to mention that. F, G, everything is smooth here. And so I can use a chain rule to differentiate E with respect to alpha. So let's do that. We have dE over d alpha at alpha equals 0 equal to the partial derivative of F with respect to alpha at 0. And then plus the chain rule, so the derivative of F with respect to F to X evaluated at 0 and X naught applied to the derivative of X with respect to alpha. Okay, that's the chain rule. That's one. But I also have other relations. The first one is that as X naught at alpha equals 0, X naught satisfies a critical an optimality condition. Okay, so if I write it down, so the optimality condition satisfied by X naught, it's the one we had before, that is the gradient of F with respect to X at 0 X naught is equal to the adjoint of the derivative of g with respect to x evaluated by at 0 and x naught star times lambda naught, which is the Lagrange multiplier for x naught. Okay. And then we have another condition, the fact that for all alpha, x of alpha satisfies this condition. And so we also have for all alpha, g of alpha x alpha is equal to 0. And we can also apply the chain rule to this condition, which gives that dg over d alpha at 0 x naught plus the derivative of g with respect to the variable x evaluated at 0 x 0 and applied to the derivative of x with respect to alpha, this has to be equal to 0. Okay. And now we put everything together. We put everything together. We have that the derivative of E with respect to alpha at 0 is, so this term we keep it. Yeah, maybe I should make one comment. Okay. We could stop here, okay? Here we have the derivative of E with respect to alpha, we are good, okay? The problem, if you want to evaluate this quantity, you need to evaluate the derivative of x with respect to alpha, okay? And perhaps it's painful to do that, okay? And in practice, it's painful because if you want to, for instance, you solve Hartree-Fock, if you want to differentiate the Hartree-Fock state with respect to some external parameter, you have to solve, it's possible, but you have to solve a large linear system. So it's, we call that coupled perturbed Hartree-Fock equations, but it's a big thing. You do it if you need it, but if you don't need it, you don't want to do that, okay? And what is nice with the formula I'm going to write down is that, in fact, you can bypass the computation of this term to get the derivative. Okay. So this is d alpha at 0 x 0. And then what you do is you replace this guy by that, because in fact it's a gradient. In fact, huh? You can also say that it's a gradient. The same, okay, because it's a scalar function. So we can put the gradient, and here we are. We are in V. It's the inner product in V. So you replace the gradient by this term. So this is what? This is d x g 0 x naught star applied to lambda naught and applied to dx, the derivative of x with respect to alpha. We are still in V. And now what do we do? What do we do now? Yes? No, the scalar product is not equal to 0. Right, yes, exactly. So what I'm going to do is I take this, it's a linear map, okay, I put it on the other side. And if I put it on the other side, I obtain lambda naught and then dxg0 x naught apply to dx over d alpha. Okay, that's why adjoints are useful. Okay, when you have an adjoint, you can put it wherever you want, where is the most convenient for you. Okay. Now, last step, just replace the right-hand side by this guy. Yeah.
Yeah, I didn't see very well what Antoine was talking about. But the gradients, is it related to that, the adjoint?
Yes, absolutely. Well, it's another, well, the adjoint, exactly. The adjoint for instance, it's possible to use adjoint method to differentiate a function depending on parameters. It's basically the same idea. It's always to put, yes.
I was wondering.
There are some similarities, yes.
Just exactly to avoid what you.
Yeah. There are some connections with what. So Antoine's point was about computing the derivative of a function depending on many variables, basically in one shot, and it's a very, very similar technique. It's based on adjoint states. Okay. Yeah. And so now I just replace this guy by that guy. So that's lambda 0 dg over d alpha of at 0 and x naught. So this time here we are the inner product in W, same here. And what's that? What's that? Looks
Stationary condition of the Lagrangian.
Yeah, it's related to the Lagrangian. And what you get, in fact, if you it's the derivative of the Lagrangian with respect to alpha evaluated at 0 x0 lambda 0, where the Lagrangian is this time a function of r times v times w to r, and which associate to some alpha x and lambda L of alpha x lambda, which is f of alpha x minus lambda g of alpha x inner product in W. Okay.
It's like you extend the Lagrangian to including more dimensions.
Yes.
And you do like partial optimization of some of them.
Yeah, so you can think that as an external parameter. It's an external parameter of the Lagrangian. The variational problem is set for any value of the parameter only with variables x and the Lagrange multiplier lambda. And alpha is an external parameter that you add to the Lagrangian. So this formula is extremely important in quantum chemistry. Okay, it allows you to compute derivative, external derivative with respect to external parameters with basically no cost. Okay, in variational methods, but it works the same for non-variational methods using the adjoint trick again. Yeah, so here. The adjoint is somewhere hidden here, but for non-variational methods, such as a couple cluster, it's really an adjoint method. You use an adjoint method to differentiate the equations.
If I do the CI calculation translated,
Yeah.
CISD, and I want to compute the derivative of the molecular orbital.
That's different.
So
if you want to compute the derivative, okay, so that's a good point. So here is to compute the energy. If you want to compute the derivative of the state, which you need if you want to compute, for instance, second derivative of the energy with respect to parameters or third derivative. So as you know, there is this Wigner rule, which tells you that if you want to compute the derivative of alpha with respect if you want to compute the case derivative of E with respect to alpha, you need some derivative of the state. And the Wigner rule says that if you know the nth derivative, if you know the derivative, so let me write that down because it's important. It's called Wigner's 2n+1 rule. So if you know the derivative of alpha, x alpha at 0 up to order n, you can compute d k e over d alpha k at 0 up to order 2n+1. Okay? That's extremely important in quantum chemistry. All quantum chemistry codes are based on this formula, on this assertion. Okay? And here we just use Wigner's rule with n equals 0. Okay, tells you that if you don't know any derivative, still you can compute the derivative of the energy up to order 1. It's what we just did. Okay. If you want to compute the second derivative, like polarizability is the second derivative, you need the first derivative of the state. But if you have the first derivative of the state, you can compute the third derivative. So the hyperpolarizability, order, whatever, okay? Or cross derivative with respect to an external field and a magnetic field, and I don't know, something else, okay? Right? Yeah.
I was wondering if there is some connection between that and the Lagrange-Euler equations, maybe? Because
Lagrange equations.
the full derivative on one side, partial on the other side.
Okay, that's yeah. So you mean the Lagrangian formula in classical mechanics? Okay. So there are similarities in the sense that the Lagrangian, so it's okay, let's say that the first answer is not really, but
Maybe.
Somehow. Okay. Yeah. It's yes.
It's something that so if you could explain what happens if we do coupled buffer, because
Yes.
let's say if we do a CI and we
Yeah.
optimize the orbitals for its geometry,
Yeah.
that really this is
Yeah.
exactly that. But if I do coupled buffer,
Yeah.
I don't calculate the energy by doing a minimization.
No, absolutely not. But you solve an equation. You solve an equation, and then you can use. Okay, I put that in the notes. Okay, I don't have time to really go through it, but I will put it in the notes if you want. With coupled cluster, what you do is that you solve an equation which depends on parameters, and then you use this guy to compute the coupled cluster energy. It's what you do. Okay. So what you have to do is to consider this equation and use an adjoint mode. So what Antoine was telling you about yesterday, to compute the derivative of the solution with respect to alpha without at a low cost. Okay. And this is the adjoint trick. Okay. The adjoint trick is very general. In fact, it allows you to compute derivative with external parameters by just solving an adjoint problem. Okay, so basically at twice the cost of the evaluation of the function. Let's say that here the cost is really 0. the additional cost is 0. In couple cluster, it's the same cost as solving the CC equations.
Compare with what you wrote, the constraints, like G, like the constraint for the orbitals plus the couple cluster equations.
No, you don't put that in the constraint. You shouldn't see that as a constraint. In couple cluster equation, you solve an equation and then you compute an energy. And the question is, I solve an equation which depends on parameters. How can I get the derivative of the solution of the equation with respect to the external parameter? You don't should think in terms of Lagrangian in this case. It's really not, yeah, but it's completely not necessary. Not necessary. It's what I try to, I argue with, yeah, but you don't need that. So I put that in the notes because apparently it's not so well known.
Like when they want to compute the derivative, they use the Lagrangian.
Exactly.
But it's not necessary at all. You are not solving a constraint optimization problem. You're solving an equation. It's different.
There's always been problems.
Yeah, but for a reason, because it's completely not necessary. You shouldn't do that. You shouldn't write the equation in these terms. It's completely different from what we are talking about. Here, there is no Lagrangian. You compute the derivative of the solution to an equation with respect to external parameters. Nothing to do with constraint minimization. I put that in the note. I have already written something about that. I know, but
because we have non-partial methods, this is where we learn about these things.
yeah.
Because the theory response theory is just
No. It's not Lagrangian methods like that. This is for constraint optimization problem or dynamics on manifolds, blah, blah. But the couple cluster is about, as Fabian told us, and also Hassan, it's about solving an equation, okay? It's not solving a constraint optimization problem. Okay, so that's one. Now let me drink first. And then let's talk about equilibrium states. Equilibrium states. So let's start by considering a problem which looks familiar to those of you who study a bit of statistical physics. I want to find the minimizer of some function S, depending on X. So lowercase s and capital S. And under some constraints, we have X is a vector of Rn. I impose that the Xi, its components are between 0 and 1. I impose that the sum of Xi is equal to 1. And that the sum of Xi epsilon I is equal to E. Okay, and here epsilon, the epsilon I are real numbers. And I assume that epsilon 1 is lower, is lower than epsilon n. Okay. So what's that? The what?
Ensembles.
Ensembles, yes. And let me specify S. It's minus KB sum of Xi log of Xi. So the entropy. Okay. And it's not a mean because in physics it's a max, so it's a sup. Because I'm always confused because in math entropies are convex and we minimize them, while in physics, entropies are concave and we maximize them. Right. I'm not sure about the sign now. X log x is this way, so that's x log x, and so the entropy is like that, so this is good. What? Is it wrong? Alfred, expert. I think it's okay, good, all right. Okay, fine? Yeah. Okay, so that's something similar to this case, except that in this case, well, the function I minimize does not depend on the parameter, okay, but the parameter is in the constraint, okay, so it fits into that. It fits into that, except that now I have inequality constraints, and this function is not really smooth at zero in the sense that it's yeah, it is its derivative blows up at zero. Okay, but there is something we gain is that this function, in fact, is strictly concave. Okay, if I draw this the function just for one xi, okay, this function is something like that. An infinite slope here, something like that. Okay. So this function is strictly, in fact, strictly concave. And if I have a strictly concave function, if there is a maximizer, this maximizer is unique. That's for sure. Okay. So these constraints are a bit of pain, but what we are going to do is to ignore them and see if we can find a critical point. And it's another nice properties of concave or convex problems. For a concave problem, if you find a critical point, then you're sure that it is a maximizer. Likewise, if you find a critical point of some convex function, you are sure that this is a minimizer. Okay? So what we are going to do is to ignore the inequality constraints. So let's ignore the inequality constraints and seek a critical point of S on ME, which is the set of X in Rn, such that the sum of xi equal 1 and the sum of xi ei equal E. So I can write that down. So this set is quite simple, okay, because this is the equation of an hyperplane. This is an equation of another hyperplane. And so I know this is, in fact, a codimensional two. What? Yes, thank you, epsilon. And this is, in fact, codimension 2 linear space, okay? But it still fits our formalism. You can write it as g of x equals 0, where g ex equal sum of xe minus 1 and sum of xi epsilon I minus E. So I was telling you that we have two linear constraints, scalar linear constraints, and therefore that it's a codimension 2 linear space. But for that, I have to check that these two are linearly independent. Otherwise, it's not the case. And for that, one way to go is to compute this. as we do in the general case. Okay, so what's that? So what's that? So this is so G is from R to Rn to R2. Okay.
Is that before the strict inequality of epsilon 1 and epsilon n?
Yes, exactly. That's what I'm going to show. Yeah, but
Okay.
you're right. Okay, so what's that? That's a 2 by n matrix. And here I have the derivative of this condition with respect to the xi. So I find 1, 1, 1, 1. And here, as the derivative of this condition with respect to the xi, I find epsilon 1, epsilon 2, epsilon 3, epsilon n. Okay, which is a matrix of size 2 times n, as expected. And to check that this matrix is surjective, I need to just to show that it is of maximal rank. And obviously, because of this condition, this matrix is of maximal rank. Okay, if it was not of maximal rank, this vector would be collinear to this one, meaning that all the epsilon I are equal. Okay, so are the epsilon I are not equal, then this matrix is full rank. So I can apply the theorem I have. Okay, I have the right assumptions. So to get the critical points, so if x is a critical point of S on ME, we have so the derivative, the gradient of S at point X is equal to dx g of E transpose applied to lambda 1 of E, lambda 2 of E. Yeah. And so this is a Lagrange multiplier. Let me write it x of E to emphasize the fact that to highlight the fact that it depends on E. Okay. And what is the gradient of that? So I have to differentiate that. So I do it component by component. So this is negative KB. KB is the Boltzmann constant times the derivative of that. So this is log xi plus 1. Okay. Okay. And equal to this applied to that. So this is just lambda 1 of E plus epsilon E, lambda 2 of E. You agree? This one? Because I transpose this matrix. So if I transpose this matrix, and then I forgot the x of E, but the x of E is in fact, so this is 1, 1, 1, 1, and epsilon 1, epsilon 2, epsilon n. So when I apply that to this vector, I find that. Okay. And now I have an expression of xi of E. xi of E is simply you the mass, and you find that this is of the form exponential negative epsilon I over kb T of E divided by Z of E with, so what is this T of T here? T of T is the inverse of lambda 2 of E. Yeah, so T of E is the inverse of lambda 2 of E. That's the temperature, okay, physically. And Z of E, which depends in fact of T. No, Z of E depends of T through T of E. This is just the sum of E from I equal 1 to N of exponential minus epsilon I divided by KB T of E. Okay, so this looks familiar. Okay, this is a Boltzmann weight. Okay, so the Boltzmann weight comes from computing the maximum of the entropy. So this is a statistical entropy under some constraints. And physically, the constraints, so the xi are the probability of occupying the state I of energy epsilon I, and this is the average energy of the state physically. Okay. Yes.
It's like magic that we get the inequality constraint at the end for free.
Yes, because of this, in fact. It's because of that's a very good point. It's because of the concavity. Because you are concave, then there is a unique maximizer, and if you can find it in the set of points which do not saturate the constraints, then it's a maximizer. Yeah, and that's a very good point. The inequality constraints xi are satisfied. And so we are sure that it is the maximizer. Okay, because
means it cannot be like this.
strictly concave means it cannot be like that. If it is, this is a concave function, and in this case, any point here is a maximizer. Okay. Strictly concave is something like that, and you just have one maximizer. Okay, and so
Okay, you're not sure that the inequality constraint is satisfied.
no, but I mean, here I'm kind of lucky, because what could happen if you have so if you have a function which is like that, for instance, so this one is strictly concave, but its maximum is here, and at this point we don't, the derivative does not vanish. Okay. The thing is that here, basically, the maximum is inside the range 0, 1. Okay, so that's 0, that is 1. Huh? Okay, so I impose that the state must be in there, but in fact, due to the shape, it has to be in there. Okay. Okay, so what does it tell you? What does it tell you? It tells you that the temperature is in fact a Lagrange multiplier. Okay, the Lagrange multiplier of the fact that of the constraints that you have fixed the average energy in your system. Okay. So 1 over T is a Lagrange multiplier of, and if you apply Feynman theorem, what do you get? Is that if you differentiate S of T with respect to E, what do you get? You get, if you just apply Feynman theorem, and you find that what you get is the Lagrange multiplier corresponding to the second constraint. Okay, so this is this guy. And what's that? That's 1 over T. And then you recover a formula that maybe you can find in some thing like that. Okay, statistical physics. No, you recover with statistical physics a formula that you have in thermodynamics. Okay, so the Lagrange multiplier. The temperature is a Lagrange multiplier. The pressure is also a Lagrange multiplier due to the fact that you fix the volume. The chemical potential is also a Lagrange multiplier due to the fact that you fix the number of particles, okay, and so on and so forth, okay. Yes. 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 Yeah. Absolutely. Okay. Okay, so now one last thing about that. If now you have a system composed of two non-interacting subsystems, which can exchange energy. So then the entropy, so you give a given energy to the whole system, and the energy has to distribute between the two systems, two subsystems. And how does it do that? What you do is that you take the minimizer of the entropy of the first system, you put an energy E1 in the first system, an energy E2 in the second system, and of course, E1 plus E2 must be equal to E. And this is not the infimum, sorry about that, this is the supremum. Okay. Now you can rewrite that as the supremum of S1 of E1 plus S2 of E minus E1 with respect to E1. At the supremum, you need to, the derivative is 0. So the derivative with respect to E1 of S1 at E1 plus the derivative of that with respect to E1. So that's minus the derivative of S2 with respect to E2 evaluated by at E minus E1. So this is E2, this is 0. And so it tells you that the derivative, so this is the temperature. And so this gives you that the temperature of the first system is equal to the temperature of the second system. And so the energy is distributed in such a way that the temperature equilibrates. Okay, so that's also something completely generic. if you take two, if you decompose your system in two non-interacting subsystems, but which can exchange here the energy, but it can be the number of particles, it can be the volume, then the Lagrange multiplier equilibrate. Okay, and this is why if you if you put two systems together, close together, the temperature will become the same, the chemical potential will become the same, they can exchange particles, and the pressure will become the same if they can exchange volume. Okay. So Lagrange multiplier is something very physical, in fact. So it's not just a trick, okay? We started from the Lagrangian trick where you don't understand anything. It's just a cooking recipe, which is absolutely not clear. And what we discover together is that, in fact, the Lagrange multiplier has a very nice geometrical interpretation, okay? Since you do that, and on top of that, when you let your system depend on parameters, then the Lagrange multiplier is in fact the derivative of the constraint of the quantity you maximize of the let's say the energy that you minimize or the entropy that you maximize with respect to the external parameters. Okay. Okay. So that's all I wanted to say about Lagrange multipliers. And let me finish with a few words about the Grassmann manifold. Yes?
So, I don't but you remember the first two examples that you gave?
Yeah.
So what was the problem with the Lagrange?
The first is that dg at point x was not surjective.
Yes.
Yeah, it was 0. It was not surjective. And then everything falls down, falls apart. Yeah. But I think that even if it works, it's nice to really understand what's going on. Okay, not just apply your cooking recipe and things. All right, so last point, is about optimization on Grassmann manifolds. So what is a Grassmann manifold? So I assume for simplicity that that the overlap matrix is an identity, okay? This is that. Okay, is what you get. It's a minimization set of Hartree-Fock or Colsham when the density matrix, the overlap matrix is equal to identity. If the overlap matrix is not equal to identity, you can always get back to that by change of variable, or you can study directly the manifold where you have PSP equal P and trace of SP equal N. Doesn't change anything about the geometry, just a small deformation. It's not a big deal. Okay. So just for simplicity, I assume that identity, the overlap matrix is identity. Okay. So there are many things to say about this manifold. I just have about 15 minutes, so I will be brief. But I have, yeah, some notes about that. Okay. So Antoine already mentioned a few things about it. One important thing is that, so what's that from a linear algebra perspective? So a symmetric matrix which satisfy p square equal p is called an orthogonal projector. Okay? And if the trace of p is equal to n, it's a rank n orthogonal projector. Okay, so what's that? That's a set of rank n orthogonal projectors. So you should see that as, so you are, let's say, in the three-dimensional space. And you select, for instance, a plane going through 0. Up, this is a plane. And P is the orthogonal projection, represents, it's a 3 by 3. So here, if I take NB equals 3 and N equal 2, so you should see an element of P, a matrix in P, as an orthogonal projector. So you are in the three-dimensional space, okay, x1, x2, x3. You select some plane, and you consider the matrix, which is a matrix of the orthogonal projector on the plane. Okay, I take some x, and this is px. Okay, geometrically, it's what it is. Okay, and if I change now n, so x1, x2, x3. So now I have a one-dimensional line, straight line, and I project my point x on the straight line. Okay. Well, okay. No, I'm not sure it's clear. Okay. P of x. And here, this picture is for NB equals 3, N equal 1. Okay. And just to be clear, okay, so this is really the thing in okay. And this is on which you project. I just, okay, maybe I can erase that. Okay. All right. Okay, this is a geometrical picture of what's going on. And but you can do that for any dimension NB and any n, provided n is between 1 and NB minus 1. Otherwise, it's a bit trivial. Okay. And basically, this manifold, so because it is a manifold, and it's basically the same as the n dimensional linear subspaces of R and B, and this is which is really called the Grassmann manifold. Okay. If you open a book of mathematics, you will find that the Grassmann manifold is the set of n-dimensional linear subspaces in R and B, but it's the same. You can completely characterize in one-to-one correspondence an n-dimensional linear subspace of RD and the projector, the orthogonal projector on this linear space. Okay, so all this is equal, that's the same. Okay. Okay, so now I could say, okay, now I have two constraints. Let's call it G1 and G2. So I create a G which goes from R NB times NB symmetric to R NB times NB symmetric times R and associated to some P, the two constraints P square minus P and trace of P equal N. and write a Lagrangian and so on. But then I'm sure the theory I presented you previously cannot work because there is no way the derivative of G can be surjective because this space is bigger than this one. Yes.
You said it's the same. Yeah, every time we embed it, the manifold is something.
Yeah.
And what of that inner space?
So this is really a manifold. Okay. Now this is an abstract object, but yeah. And then the differential structure is the one that you can put using that, for instance. Okay. Yeah. But yes, this should be endowed with absolutely. You're absolutely right. This is just a set. If I want to say this is a manifold, I need to specify what is the differential structure on this set. And it turns out that it is a natural differential structure that you find if you embed that. So these two are complete. But you're right. You're absolutely right. I didn't want to talk about that, but you're absolutely right. Yeah. So manifold is not just a set. It's a set plus a differential structure. Okay. But okay, let's, yeah. Okay. All right. So, okay. So now, so this means that I cannot use this trick to show that this is a manifold. Okay. I need to do something else. So what can I do? Maybe I can go back to the original definition of the manifold. That is, here I have a set which is embedded in this set. If I'm able to find a local chart, okay, or a system of coordinates, then I'm good. Okay. And what is so let's start to do it around some specific rank n orthogonal projector, which is this one. Okay, so you agree. So this is a matrix of nb minus n and nb minus n. So this is obviously symmetric nb times nb matrices satisfying this and that. Okay. So what is nice is that it's possible to find, so I call NV the number of what you call in chemistry virtual orbitals. And then you have a nice you have a nice system of coordinates. You go from n v times n into this. And you define P of x as the following matrix. So you put x here, x transpose here, and then you put some formula. With more space, in fact. Oh, okay. Half of in plus in minus 4 x transpose x to the 1/2. And here you put half of inv minus inv minus 4x transpose to the 1/2. Okay? This is a block matrix. And in fact, this defines a local system of coordinates. So the proof is in the notes. Huh? Defines a local system of coordinates around P naught. If you put X here, you have no choice. If you put X here you need X transpose, obviously, because you want a symmetric matrix. And here you have no choice. It must be that if you want to find, if you want to this matrix to be in the set of orthogonal projectors. And in fact, so you cannot do that for all X. You need this matrix to be defined, okay? Because you take the square root, and so you need to take the space of matrices such that, for instance, the Frobenius norm or some norm is lower than some eta. Okay, it's a local system of coordinates. It's quite big, okay, because what you need is that the matrix identity minus 4 X transpose X is non-negative, okay, is positive, okay. That's all what you need. So it's quite a big, big map, okay. But it's a way to completely parameterize your system, okay. But there is another way, okay. Well, there are many ways, in fact. And so from that, you can find that the tangent space to M at P naught is in fact the set of matrices Q of the form 0, X transpose X 0. With X in R and B times N. But you have another system of coordinates. And the other system of coordinates is the following. You go from R NV times N. So here you can put everybody, or at least you can define this for everybody. You go from here. And you take a matrix X, and you compute P naught. No, you compute exponential of 0 X minus X star 0 then you put P naught. And then you put exponential 0. And well, the sign, one of the sign is wrong. Let me check which one is wrong. You know it? No, one of these here I have yeah, one of the minus sign here has to go to the other one, but okay, yeah. So it's minus here and yeah. Okay, right.
Like going back to the Stiefel manifold in some sense?
It's going back. I'm going to talk about that. I'm going to talk about that right now. Okay, so this map is nice because here and this is belongs to M. So how can you see that it belongs to M? So first, here you have the exponential of an antisymmetric matrix. And the exponential of an antisymmetric matrix is always an orthogonal matrix. Okay? Is this U here? It belongs to the orthogonal group. That is a group of matrices U such that U transpose U equal identity. Okay, because every time you take the exponential, an exponential of an antisymmetric matrix, you get an orthogonal matrix. Okay. And here, obviously, you have the same. So in fact, this big guy is U P naught U transpose. Okay, because this is a transpose of, because of the sign is changing, this is this. Okay. And any P of this form is indeed an orthogonal projector of rank 1. Okay, because if you take the square, well, first it's symmetric, obviously. If you take the square of that, you have this multiplied by the same, but let me write it. P naught U transpose, then U P naught U transpose. This is identity. P square equal P naught square equal P naught, and so this is P. And the trace of P is the trace of U P naught U transpose, but remember this, you have the cyclicity of the trace. So this is the same as this. This is the identity, and the trace of P naught is N. Okay. So this is another parameterization which is used very much, in fact, in quantum chemistry, in particular to design second-order algorithm. Maybe you know the Bax-K quadratic algorithm for solving Hartree-Fock. Okay, it was designed a long time ago in the 60s, and it is based on this representation of the Grassmann manifold. Okay, because now you're good, because what you can do. Okay, so this is a local system coordinates around P naught. But now, if you want, if you have another P, a generic P can be always decomposed at some U P naught U transpose. Okay, always. And therefore, to get a map around, or let me put let me call it yeah, let me call it I don't know, U tilde to differentiate this one. Okay. You can always decompose P as follow, and a local system of coordinate around P is given by U tilde and U tilde transpose. Okay. Okay. This gives you a local system of coordinates around P, because if you take x equals 0 here, you get U tilde P naught U tilde transpose, and this is P. Okay. Yeah.
When they do density matrix,
Yeah.
Because it works very well, but it's more expensive than the usual.
It's quadratic. It's quadratic, so it converges in very few iterations when you are close to the solution, but it's costly because you have to compute the second order derivative, the Hessian of the energy. But basically, it's exactly what they do. Okay. Well, and in fact, they don't store all that. They just store that, which is a unitary matrix. Okay. So the algorithm for quadratic convergence algorithm, what you store is a set of matrix. So at iteration k, you store a unitary matrix. Then you do one step of Newton algorithm on this function. So this is F. This is, you do one step. So this is F at iteration K. This is the Hartree-Fock energy in the density matrix formulation of this. And then you have the exponential of this. Then P naught, exponential 0 minus x transpose 0, UK transpose. Okay, so this is a function defined on a vector space. So you do one step of Newton, starting from x not equal 0. So you do one step of Newton. You get some xk, and then you compute uk plus 1 equal uk exponential of 0 xk minus transpose 0. And you iterate. Okay?
So you agree that so here you don't need the molecular orbitals.
No.
Because if you write
But well, you don't need. Yes and no, because if you compute the gradient of that and the deviation of that, very quickly, you will see that it's very convenient to express the matrices and the gradient deviation in terms of occupied blah blah. Okay, but in principle, you don't need. You just you iterate that.
because if you write P as 6, that's good.
Yeah.
Actually, here you do a double rotation of the left of the right, but you could see that as a single rotation of
Yeah.
P or C is
Yes. Yes. Exactly. Okay. And why is it? Why can you do that? And it's related to the question of Loic. In fact, is that the Grassmann manifold has a very nice structure. So let's say M. It can be identified with a quotient manifold, which is a quotient of this orthogonal group with the product of this orthogonal group. So physically, what does it mean? Is that you represent your system by a set of orthogonal molecular orbitals, that's your matrix U. The first n columns correspond to occupied orbitals. The last NV columns correspond to virtual orbitals. Okay, so you represent your state by this. And this quotient tells you that if you make a rotation, this is a rotation that, is a unitary of the orthogonal of the occupied orbital, you don't change the state. Same here. Okay. And the nice thing is that, so this also explains why you can write things like that. And in fact, this is also, so the Stefan manifold quotiented by O of n. Okay. So the Stefan manifold is because, okay, here you work with both occupied and orbital and virtual orbitals. In the Stefan manifold, you work only with occupied orbitals, but you know that you can you can rotate internally the occupied orbital. It doesn't change anything. So what's nice with this? What's nice with this framework is that, in fact, so here I explained to you how to do second order optimization, okay? But second order, as you said, T2 is very, very costly. And so you don't want to do that. And so for direct optimization, it's better, as Antoine said it also yesterday, it's better to use first order methods, okay? But it's first order methods on manifolds, okay? And if you want to do first order of manifolds, you need to find ways to move on the manifold. Okay, and for that, you need two things. You need a retraction. So Antoine talked about that yesterday. And you need also a transport map to transport tangent vectors at one point to tangent vectors to another point. Because, for instance, in the conjugate gradient algorithm, so you are somewhere, you go, you have a descent direction. Then you go, you reach this point. You compute the gradient, and you compute the opposite of the gradient. And then the direction you choose is not the direction opposite to the gradient. It's a linear combination of this vector and that vector. And then you find some descent direction, and then you iterate. Okay, that's a conjugate gradient algorithm. If you want to do that on a manifold, you are there. So your descent direction is there. You move around along the descent direction, and then you need to get back to the manifold. So you do that with the retraction. Then you compute the Riemannian gradient, which is the opposite of the Riemannian gradient, which is a point on this tangent space. But then what you need is to put this vector, which is in this tangent space, to that tangent space. And for that, you need what is called a transport. Okay, and it turns out that if your manifold has this structure, it's quite easy to design natural retractions and transport. Okay, there are other ways to do that, but if your manifold has this structure, it's quite easy. Okay, and in a paper with Laurent, we extended that to, and with also Filippo Liparini and Tommaso Notoli, we extended that to Cancès CF also, and restricted open shell RT-Fock. Okay, so geometry is very important when you do optimization on manifolds. Okay, yeah.
So in quantum chemistry, we know this exponential parametrization.
Yeah.
And so we say, okay, we have identified non-redundant parametrization. And so we can forget about the constraint.
Well, actually, it is redundant. It is redundant, but you don't care. But it is redundant because if you apply, it's like if you so this is cos theta sin theta minus sin theta cos theta. Okay, so if you replace theta by theta plus 2 pi, it's the same matrix. Okay, but doesn't matter. Okay. It's redundant, but it's fine. Okay. But yes, go, please go on. Yeah.
No, so I'm just saying that, okay, we use the exponential parametrization.
Yeah.
And then we say we don't care about the constraint anymore.
Yeah, that's correct.
And we do exactly the same as the M constraint.
That's correct. But there is a catch. The thing is that if you want to compute the gradient and the Hessian of this matrix at x equals 0, it's simple. Because at x equals 0, it's easy to compute the gradient and the Hessian. If you want to do that at another point, then it's a pain because you need to compute the derivative, the second derivative of the exponential. If you have just a real number, you know that the derivative of the exponential is just you know it. Okay. But if you have a matrix, then it's much more complicated because the matrices do not commute. Okay, and so it's BCH Baker by formula, BCH formula. Okay, and it's a pain.
Always want in practice at 0.
Yes, because you just do one Newton step and then you go. Okay, but it's good if you do second order algorithm. But if you do first order, what you want to do is that you have a descent direction, and then to do conjugate gradient, you transport or BFGS. Okay, you transport the descent direction to another point. And if you want to do that, so how do you do? Okay, if you change, because here what you do is that you change when you apply this algorithm, you change your local system of coordinates at each iteration. Okay, so first you are here, first iteration you are here, second iteration you are there, and so on. And so you have to transport everything. Okay.
So for example, if you start doing Taylor expansion of the exponential, you out of the manifold. So
Taylor expansion of the manifold. Yeah, that's right.
out, and after you need to find a way to get back onto.
I mean, but you can define the Riemannian gradient, the Riemannian Hessian, as Antoine mentioned yesterday. So in this case, you stick to the you stay on the tangent plane to the on the tangent space to the manifold. Then you need a retraction in a way. But here you have a retraction. Okay. But the point is that yeah. So basically, if you change your local map at each iteration, you need to transport everything you have to the other map, okay? And what is difficult to transport is the descent direction, because it's a vector, and you have to know how to transport a vector in a local system of coordinates to another system coordinate. So parallel transport is one way to transport a vector. There are others. It turns out that if you are in this framework, the parallel transport is easy, but usually it's difficult to do parallel transport, because to do parallel transport, you need to solve basically the geodesic equation and an equation along the geodesics, okay? And this is solving an ordinary differential equation, and you don't want to do that, okay? Here, the nice thing is that on the orthogonal group, the geodesics are very, very simple. Okay, this is written in the notes. And so you can do parallel transport on this group, on any Lie group. In fact, on Lie group, it's easy to do parallel transport and all that. And because of this quotient structure, you can transport, you can induce, you can find the closed expressions for the vector transport for the parallel transport on the quotient manifold. Okay, so Louis, last question. Okay. Okay. So thank you for your attention.